In this lecture we are going to discuss about the MOS physics. Why this is important? This is important because finally we wanted to understand the MOSFET. So for MOSFET, MOS actually is the heart of the MOSFET. So before going to the MOSFET, we need to understand the MOS. So this is the schematic diagram of the MOS structure. So we have a p-type semiconductor wafer, then we have a oxide layer, and then we have a metal layer. So this forms basically MO and S, metal, oxide and semiconductor. So whenever we are understanding any junction physics, I already told you in the previous lecture that we need to understand the built-in potential, we need to understand the depletion region width, and we need to understand the depletion region charge. So in this lecture we are going to understand these three concepts as far as the MOS is concerned. So these are the band diagram of the metal. So we know metal, in case of a metal, the topmost field energy level is known as the Fermi level, and the distance between the free space and the free vacuum level to the Fermi energy level is known as a work function of the metal. Then we have a oxide. In case of a oxide, we have a valence band, we have a conduction band, and in between you have a energy band gap. The energy band gap of the oxide is very large. It is around 8 electron volt. However, this is the electron affinity of the oxide. The conduction band to the Fermi level distance is known as the electron affinity. However, in case of a semiconductor, you have a conduction band, you have a valence band. Since it is a silicon, we have a band gap of 1.1 electron volt. This is the distance is known as a Fermi potential, which we already know. This is equal to kT by Q ln Na divided by Ni, or if you want to neglect the negative sign, then this is a Ni by Na. If you will keep it as a Na by Ni, you need to put the negative sign over here. Okay, so now what will be the built-in potentials? First question is, what will be the built-in potential in case of a MOS? If it is a P and N, we already know the built-in potential would be kT by Q ln Ni Na Nd divided by Ni square. This we already know. In case of a metal and semiconductor, we need to understand what is the work function of the metal and what is the work function of the semiconductor, meaning this distance. So this would be Q phi S. What would be the Q phi S? Q phi S will be the Fermi level to vacuum level distance. So this distance basically would be Q chi, that means this distance plus half of the band gap, meaning Vg by 2, meaning 0.55, and whatever the Fermi potential is. Let's say the Fermi potential in this case is given as 0.2. So what would be the work function of the semiconductor? The work function of the semiconductor would be 4.9. 4.15 plus 0.55 plus 0.2. So this would become 4.9. So what will be the built-in potential? So the built-in potential will be Q phi m, the work function of the metal, minus the work function of the semiconductor. This is 4.1 minus 4.9, which is equal to minus 0.8 electron volt. And this 0.8 electron volt is also known as the flat band or flat band voltage, because this voltage is basically corresponding to the potential difference which is applied externally between the gate and the substrate. So when you apply the external voltage, which is equal to 0.8 volt, then what happens is the bendings of the energy band near the surface, so that becomes the flats, which we can see in the next slide. So this is the bending. So basically this is the bending occurs. So this bending occurs and this bending occurs. So when you apply the voltage which is equal to the built-in potentials, so these becomes flat. So we also call the VBI as a flat band voltage. Flat band voltage. Now let's understand the another concept, which is a depletion region width. What is the depletion region width in case of a MOS? So we already know that in case of a PN junction, the width was if it is a heavily doped one side, then the width was 2 epsilon Si divided by QNA into VBI. And what was the VBI? So the VBI was the difference between the Fermi level one side of the junction and the Fermi level of the another side of the junction. However, in this case, since the depletion region is only extending into the semiconductor, because the other side you have a metal. So what will be the depletion region width? So the depletion region width will be 2 epsilon Si divided by QNA, and here you wanted to have a VBI. What was the VBI? VBI was the distance between the Fermi level. So here you had a junction, and one side you had one Fermi level, another side you had another Fermi level. Now here you have a junction over here, and let me rub it just a second. So you have a junction over here, and the Fermi level, the depletion region is this. So at the depletion region, and you have the Fermi level, the distance of the Fermi level is phi, let's say f, the bulk Fermi level, and at the other end of the depletion region you have, let's say the Fermi level is defined as phi s, the surface Fermi potential. So what would be the xd? The xd would be 2 epsilon Si divided by QNA, then phi s minus phi f. Okay, and if you wanted to find out the depletion region charge density, so definitely the depletion region charge density would be QNA into NXD. So if you would take QNA inside, so it would be Q square NA square. So finally you can cancel out the QNA from the denominator. You will be getting Q equal to minus 2Q NA epsilon S phi S minus phi F. Why is the minus sign over there? Because we are understanding the PMOS. In case of a PMOS, you have a acceptor charge density which is Na. So that's why you have a negative sign over here. If you have a NMOS, definitely the charge density in the depletion region would be positive. Thank you.